Okay, this is part 2 of chapter 8, talking about statistical validity of correlations. So when you're interrogating this validity, you're asking questions like how strong the relationship is, how precise, whether it's been replicated, and talking about things like outliers, restriction of range, and whether you're dealing with a non-linear relationship that's still there, but just not something you can investigate with typical correlation analysis. Okay. Effect size, this is the strength of an association. Okay, so if R is closer to 1, then that's a stronger association than if it's closer to 0, or closer to 1 or negative 1, right? It's usually more meaningful if there's a large effect size. You have more predictive power, but not to say that small effect sizes are worthless. If you have a small effect size, but if it compounds over many observations, then it could lead to a big effect. Or sometimes in things like sports, for example, like swimming, things are won by a fraction of a second, and small effect sizes can make a big difference in the outcomes. Okay, this is kind of a guide for interpreting the magnitude. Now, this is rough. But these are just some general guidelines. Very weak would be like 0.05 / negative 0.05, all the way up to 0.4. If you're in psychology studies, at least, if you're seeing R values that are higher than 0.4, then it may be too good to be true. When you're dealing with humans, data is often pretty messy, and so you're rarely going to see scatter plots that are really tightly clustered around a line. But yeah, this is just kind of some benchmarks that you can refer to for how strong a correlation is. You can compute confidence intervals for R values, and that can give you an idea of the precision of an estimate. Sometimes these are used to not only establish precision, but also to indicate whether a correlation is statistically significant or not, meaning can it be readily explained by chance variation alone, or does it indicate a real effect? And you could have a significant, if you have a confidence interval that doesn't contain 0, then that means that you have a significant correlation. If it does contain 0, then it's unlikely that what you have is probably not very far above 0, far away from 0, and it's unlikely that you can explain it explain it by a real effect. It could be just due to chance variation. Okay. Sample size, if you have a greater sample size, then that is a way that you can usually get a more precise estimate. Based on how confidence intervals are calculated, sample size is going to shrink and make confidence interval narrower. If you have the resources to get more people, then that can help you to get a more precise estimate of the R value. Okay. Replication. So in meta-analyses, analyses of multiple analyses, papers that are written summarizing statistically the results of multiple studies, then you can get an idea of what the true trend is, or the true R value in the population of interest. Right? So you may have R values around here. Each of them has some margin of error or confidence interval associated with them, and over multiple studies you can start to see that this is probably where the true R value is. Okay? There may be some studies that show up as non-significant, where this is a non-significant correlation, but overall you can start to see that there's a trend towards significance. Okay, so stronger evidence that this is a real effect. Outliers. Okay, so outliers are kind of a tricky thing to deal with in statistics, but R values are vulnerable to influence by them. So it's something that you need to watch for in your scatter plots. Okay. So this is just to kind of illustrate. If you draw a line here through these points, it's going to be mathematically there's a line that's going to fit those points best, or the average distance from the points to the line is minimized. Now if you have this line in here, it's going to tweak this line of best fit upward, and it's going to actually influence the R value, indicating a stronger correlation here than if you were to remove it. Okay? Now the effect is even bigger if you have fewer data points. Okay, so this is a very influential outlier versus this. Here, this is almost no relationship at all. Here, it makes it appear that there's a very strong relationship just because of that one individual right here. Now, what do you do with this? Depends. You first want to make sure that it's real data, that it wasn't just an entry error or something like that, that there was something wrong with your instrument and some data was recorded way outside the regular range or something like that. If it's real data, then that's a more difficult question. Some recommend maybe you report both of these in your paper, indicate that there was an influential outlier, that the relationship may not be actually as strong as it is, but it's typically not good practice to simply chuck these points and leave them out. If they're real data, then it does exist, and it could be that there's some subgroup that's worth investigating that this outlier comes from, or it could lead to some interesting questions later, but it's best not to just brush it under the rug. But you'll have differing opinions in the statistical community and in the research community on what the best practice is with outliers. Okay, the main takeaway here is that you shouldn't ignore them, and you should know that they can influence your stats. Okay. Another question is there a restriction of range? So here's an example of a scatter plot, and these are SAT scores and GPAs, just made up data from a fictitious college. Let's say that this college only admits students that have a score of 1200 and above. And you can see that there's a positive relationship here, but it doesn't look all that strong. Now, if you were to investigate this relationship without that range restriction, you'll see that the relationship is actually stronger than it appears here, because these lower SAT scores also have lower GPAs, okay, so the R value goes up. So that's a question to keep in mind. Okay. Sometimes you can't do much about it, and so there are statistical techniques that can correct for it, or maybe you could recruit more participants, for example. But yeah, something to be aware of. Okay, a curvilinear association. Okay, so this scatter plot here has an R value of 0.01. That indicates a very weak relationship, basically saying that there's no relationship between these two variables. However, if you look closely at this, you should hopefully start to see that, yeah, there is a relationship there. It's just not linear. Okay, so an R value really is only useful for telling you the strength of a linear relationship, one that's best represented by a line. This, though, is a curvilinear relationship best represented by a curve. Okay, there are other analyses that you can use that can measure the strength of a curvilinear relationship. Okay, so you'd want to use something like that rather than your typical Pearson correlation. Okay. All right, that's the end of this section.